Okay, so now we are starting a very interesting topic called recursion. And I would like to introduce this topic in a little, you can say, general way. So typically when we are dealing with recursion, in the back of the mind, what we have is problem decomposition. So whenever you are hit with a problem, the solution to which is composed of solution to the varieties of sub-problems. That's the situation when you should be thinking about recursion. And therefore, recursion has got two aspects. The two aspects are, the first is that what arguments are going to, is your recursive function going to take? So argument is what you should be worrying about first. What are the arguments to my recursive function? Okay, so what are my arguments? Second question you should be asking yourself are, what are the conditions? So conditions meaning there are typically two kinds of conditions that come up in the recursion. One is the base condition, and another is the recursion condition. So base is typically when, under what circumstances are you exiting out of recursion, and under what condition are you trapped within the recursion. So how it would look like is that if you have a problem P1, okay, and that problem to that, as I said, is broken down into solutions to its subproblems. So let's say subproblem 1 gets solved through S1. Okay, so you decompose into S1, S2, K different varieties of solutions. And then after you got the solutions, what are you going to do? The solution is going to return something. So that return, this is going to result R1. This is going to return result R2. And this is going to return result R3. And therefore, this should have the ability to recombine. The solutions from, so RK, sorry, not R3. So R1, R2, dot, 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 RK. This is the general formulation of any recursive solution. Okay, so now let's take examples. So in other words, so it went through the process, so recursion essentially went through the process of decomposition into sub-problems and recompositions of the results that are coming out of the solutions to the sub-problems. So recombination. Okay, so let's see this happen through some examples, okay? So example 1. The most common example that are given in the domain of recursion is factorial function. So what is the formula for factorial? So n factorial is represented as n times n minus 1 factorial, right? So you can see that there is a recursion inbuilt within the definition of the factorial function. So therefore, we will just follow this strategy. So first question we have to ask is that, what are we dealing with? So what is the argument here? So what is the argument for a factorial function? What does a factorial function take as argument?
N.
n, exactly. Then the next question that we are dealing with is what? We are dealing with the conditions, right? So there has to be a base condition. So what is the base condition that we know of in the factorial?
When n is 1.
Yeah, n equal to 1. You can also say n equal to 0, but I think 1 is good enough. You don't have to. So then the result will be equal to, so when the value of the argument is 1, what is the result here? What is the value that you know?
1.
The result is 1. Okay. Then the next part is the recursion part, right? So what is the recursion part? So recursion condition is n greater than 1, right? So when n is greater than 1, then what do we do? So we are working on, we assume almost that the sub problem is going to fetch me the result, right? So we say that factorial, so let's say this is your writing like this, factorial of n. So factorial of n minus 1 is going to give me some result, right? So this is going to return me some result, okay? And I fully trust whatever the result that this sub problem is returning to me. I don't have to worry about it. I just take it for granted that this has correctly done what it is supposed to do, which is solving the factorial on n minus 1. So having obtained that, then all I need is now, so this is essentially our decomposition step, because we are decomposing into smaller problem. So after decomposing, now I can recompose into the solution by taking this x and then multiplying with n, and I'm done. So if you want to see that this in action, how it would look like, so suppose you want to find out, so suppose n equal to 5, okay? So then you start with 5, and then 5 you check 5 is greater than 1. So what you're doing is that you're decomposing. So this is essentially recomposition step. So 5 gets decomposed into 4. So here we are running essentially, so when I'm circling this essentially means I'm calling factorial on 5. So calling factorial on 5 leads to calling factorial on 4. But 4 is also greater than 1. So 4 leads to calling factorial on 3, because n minus 1, right? So 4 minus 1, 3. So 3 is also greater than 1. So you keep going. 2. 2 is also greater than 1. So you again, one more step. You got into 1. Now you are hitting the base case. So once you have hit the base case, now what do? I know how to compute the base case. I know that result is going to be 1. So this guy returns 1. So once this guy has returned 1, it's essentially now at this step getting the value x here, right? And it now knows at this step how to recompose, right? And what is the recomposition step? The recomposition is you just multiply this n, whatever the current value of n, which is 2, with whatever got returned, right? So it's 2 multiplied by 1, 2. And that's the r that this factorial of 2 computes, and this guy returns back therefore 2 here. So now this has now obtained factorial of 2 back, the value back, which is 2. Now it knows how to recombine. So it just multiplies. So 3 multiplied by 2, 6. So this returns back 6 here. Again, this knows how to recombine. So it recombines by multiplying 4 with 6, that is returning 24. And then finally 5 multiplied by 24 gets recombined into 120. And so the output comes out 120. Any question? All right, let's see one more example. This is also a famous example called Fibonacci numbers. So what is the formula for Fibonacci number? Fib of n is equal to what? So Fibonacci number can start with 0 or 1, but let's say we start with 0. So 0, 1 are the first two starting points. And then we just keep adding, right? So 0 plus 1, 1, 1 plus 1, 2, 2 plus 1, 3, 3 plus 2, 5, 5 plus 3, 8, and so on and so forth. So if this is the value of n, this is the Fibonacci of n. So the 0th Fibonacci number is 0, then 1, 2, 3, 4, 5, 6, and so on and so forth. So what is the formula here for Fibonacci of n? How can we write down?
Is it n minus 1 plus n minus 2?
Exactly. So fib of n minus 1 plus fib of n minus 2. So you can see there is a recursive substructure inbuilt within it. This is the sub problem. This is another sub problem. So in this case, the only difference is that there are two sub problems that have to be composed together in the form of addition, right? So again, we can very quickly write down. So here argument the argument here is again n. The base case, what is the base case here? What are the base cases?
When n equals 1 or 0.
Exactly. So when n equal to 0, then the result that is, or the return value is going to be 0, right? So these are the two base cases, right? And when n equal to 1, then the result is equal to 1. And then the recursion case is when n is greater than 1, right? So this is basically starting from here onwards. So when n is greater than 1, then what is the decomposition step here? So we are computing x equal to fib of n minus 1, right? And we are computing y equal to fib of n minus 2, and your return, which is, so this is our decomposition step, and the recomposition step is x plus y. So this is the recomposition step. All right, so now we can very quickly see this in action also. So in this case, there are two decompositions involved here. So let's say, you can change the color. So suppose you start with 5. You want to compute Fibonacci for 5. So 5 is greater than 1. So therefore it gets broken into 4 and 3. You're calling on Fibonacci of 4 and 3. 4 is still greater than 1. 4 gets broken down into 3 and 2. 3 is greater than 1, gets broken down into 2 and 1. 2 is greater than 1, broken down into 1 and 0. 3 greater than 1, broken down into 2 and 1. 2 gets broken down into 1 and 0. Similarly, this gets broken down into 1 and 0. And then we know how to compute. We know that the Fibonacci from the base case, we know when it is 0, the result is 0. When it's 1, the result is 1, right? So we can return back. So this is the base case. So this returns 1. This returns 0. This returns 1. This returns 1. This returns 0. This returns 1. This returns 0. This returns 1. Okay. So once we have reached there, we have to now recombine. So what is the recombination step? The recombination step is simply addition. So it does 1 plus 0, 1. So this returns 1. And then 1 plus 1, this returns 2. This returns 1 plus 0, 1. This returns 1 plus 0, 1. And this returns 1 plus 1, 2. And then this returns 2 plus 1, 3. And finally, this gets recombined as 3 plus 2, 5. So 5 is the return value for Fibonacci of, so Fibonacci of 5 is equal to 5. And if you see here in this table, Fibonacci of 5 is indeed equal to 5. So you are now able to see how the recursive functions work. Typically, what I'm drawing down here, they correspond to essentially stack frames. Because when you're making function calls, all you are doing is that you are climbing up in the stack frames. And therefore, if you have to compute the complexity of this operation, now we have not discussed the time complexity theoretically, which we're going to do soon. But if you just want to measure what is the space impact of this, for example, the space impact for executing this Fibonacci is very clearly just the stack depth, because you can see that it is at one time only one particular stack frame is live, right? And because of that, the space complexity of this is going to be just the maximum stack depth. All right. But we'll cover the time complexity in a little more detail. Okay. Next, let's move on to a very famous problem called the Towers of Hanoi. So this is also a problem in your homework, but I just wanted to lay down some foundation so that it becomes easy for you to. It's not there in the homework. I'm sorry. It's there in your lab. So it's a puzzle. So what is the puzzle here? So there are 3 pegs. So there are 3 pegs. So there are 3 pegs, and then there are discs of various sizes, So you can think of decreasing sizes. So what is the problem here? That if you have disk, so that, let's say we assign this is peg number or peg identifier A, this is peg identifier B, this is peg identifier C. The problem at hand is how can we move these disks from A to B? So the condition is that we have to move from A to B with the help of C. But the condition is that at no given time, there should be a smaller disk situated below the larger disk. So in other words, if you have a configuration like this, right, that would be improper configuration. So how many steps it would take for you to maintain this and at the same time transfer the disk from A to B? So that is the problem. And of course, the problem can grow in any number of complexity because any number of n. So n is the number of disks. And then there are 3 pegs. So n disks and 3 pegs problem. Now it is easy to see how you would do it for 2, right? What is the possibility of you to move from A to B, both the disk? You can see that if you just directly move from A to B, you will immediately get into this configuration. So therefore you have to move the smaller disk to C and then move the larger disk to B and then move the smaller disk back to B. And that's how you would reach this kind of configuration in B. So you have to move all the disks. So you may be having many number of disks and you have to move all of these disks from A to B. Is the problem clear? Now you can see that as soon as the number becomes even n equal to 3, even just that seems quite overwhelming, right? And what to speak of if the number is n equal to 10? How do you keep track of this condition while you're moving things around? But you will see by using recursion, this problem becomes extremely simple. Because you are just thinking in terms of base case and just relying on the basic foundation of recursion to do the rest of the job. So let's think recursively here. So again, let's think about the arguments here. So what are the arguments here to the problem? The arguments here are, you have got n disk, n disks, and then you have 3 pegs, which are labeled A, B, and C. Remember, you use the enumeration in your last lab, the increasing and decreasing. This is a perfect candidate for enumeration because when you're calling the peg, you can call it, okay, 1, 2, 3. You can identify even with a character label, but you can also just identify them as enumerated identifiers. Any case, so these are the arguments. So you have n, A, B, and C. So what is the base case here? What is it that the easiest thing for you to do? Or what would be the easiest problem that you can very easily solve, where there is practically no brain needed?
One.
Yeah, n equal to 1. So if n equal to 1, then what should we do? What would be the resulting? So here what we are looking for, let's be very clear. What are we looking for here? It's a puzzle, right? So puzzle means we are looking for the steps. Give me the exact sequence of steps needed to achieve this, right? That's what we are looking for. So what is the step here to when you have only one disk? What is the step?
Move A to B.
Yeah, move A to B. And we can represent that step just in a simple way, like move A to B like this, right? So this essentially implies move A, or move the disk from A to B, essentially, right? Very straightforward. Okay, so now let's come to the recursion step. So what is the recursion step here? So what is the condition? Condition is n greater than 1. So what can we do when n is greater than 1? So I think one of the ways to think about is because this peg C is there, right? If somehow, let's just visualize this. So this is your A, this is your B, and this is your C, right? Suppose you have 3 disks, right? Suppose you had 1, 2, and 3, right? What is the configuration that you would like to see just before you solve the problem? What would be an ideal configuration? After all, you want to reach here, right? After all, you want to reach here, right? All the disks in this configuration have to reach here. But just before you solve it, what is the configuration that you would like to see this to be in?
You would have the 2 largest disks from A sitting on B and the smallest disk from A.
Typically, the first 2 somehow, if suppose this is the configuration, the top 2 are here, right? So if you know somehow how to send these top 2, right, into this guy, into C, with the help of B, then you know what you can do is that you can simply move this larger disk here, right? So then the next configuration would be you move the largest disk, right? So here we moved how many? We moved essentially from the first step was that we moved 2 of these, right? So here n minus 1, right? We moved 2 of these to the peg C, right? And then we moved the remaining one to B, and then from here we know, if we know how to move n minus 1 from here to here, we can also know how to move these are also n minus 1, right? So we had this configuration. So these are n minus 1 disk. So you just move these n minus 1 disks from here to here, and then we will reach clearly this configuration. So you have the largest disk and then smaller disk, and then this will appear to be T. So this is again A, B, C. Okay, so now if you want to see it, we saw it in with 3, and that is good enough for us to see. The first step was to move n minus 1 disks from A to C with the help of B. Then you moved just one, the remaining one, and then we moved the n minus 1 from C to B with the help of A, right? So we just put this down here, okay? So we can say here the first step is, so R1, the first step is what you call, okay, we didn't give any function name. So let's say TOH is our function name, which takes in arguments N, A, B, and C, okay? So these are the arguments. So what is the first step? The first step is you move these, right? This is our first sub problem. The sub problem here is that we are learning to move. So It's the headache of this recursive function to figure that out, however way it figures out, right? To move n-1 disks from A to C with the help of B, right? Because the second argument is the target. The first argument is the source. So from source to target, and the third argument is with the help of. So that's the first you can say the sub problem that we are solving. What is the second sub problem we are solving here? What is the second sub problem here? Or sub solution? It's not even a problem. Solution to the sub problem. It is moving one, right? It is moving one from A to B using C. And then the last one is moving n-1 disks from C, right? Back to C to B using A. You see, this is the final target, right? So clearly this is in the second position. So these are the decomposition steps, right? This is the decomposition step. So what is the recomposition step now? The recomposition step is going to be what? So these are generated what? These are generated some instructions, right? That move this from this to this. This has generated some move this from this to this. This has generated move, right? So these are all instructions that got generated. So the recomposition step is simply going to append, right? So append all of these steps together, right? So append R1, R2, R3. And we are done. Now let's see this in action, because it is not very satisfying to just imagine that that's indeed going to be true. The puzzle is still looking quite formidable. So let's see with 3, A, B, C, okay? Let's see how it would look with just this. So we're calling TOH, the towers of Hanoi, on this 3, A, B, C. And then what happens? This gets decomposed into 3 problems and the corresponding sub-solution. So what is because why it get decomposed here? Because n is greater than 1. So 3 is greater than 1. That was the basis, right? So 3 was greater than 1. So therefore this gets decomposed into what? This becomes 2, right? Going from A to C through B, right? That is the recursive call, right? And then moving one peg, right? One peg from A to B using C. And then what is this one? Moving 2 pegs from C to B using A, right? So this is again greater than 1 here. So this gets further broken down, right? So this becomes 1. Where are we sending? This goes from A to B using C, right? A to B using C. And this remains 1 comma A comma C comma B, moving that large one, and then moving 1 from B to C using A, right? And this is just 1, so we know how to do that. So because this is greater than 1, so this again gets broken down into 3. So this becomes 1, and then what should be? From C to A, right? Using B. And this is 1 comma C comma B comma A, and this is 1 comma A to B using C, right? Okay, so now we have got the solutions to the subproblems, and this is going to come back because if we know how to solve this, it's just one, right? So it's moving A to B. This is moving A to C. This is moving B to C. This is moving C to A. This is moving, I'm simply looking at the first two because it's just one disk, right? C to B, and then moving this from A to B, right? And what is this guy going to do? It is just going to order them, right, in sequence. It's going to put, it's just going to append these three in sequence and then send that sequence back to this guy. And then that would be followed by this guy, which it knows that this is going to be A comma B. And this again is going to sequentialize. So this is going to form this sequence. So if you see what is going to happen therefore as a result when it comes out will be essentially this would be the first, this will be the second, this will be the third, this will be the fourth step, this will be the fifth step, this will be the sixth step, and this will be the seventh step. So it takes 7 steps to get to this configuration that we want. Any question? All right. Let's move on. So I hope the recursion, the basic introduction was clear. If not, please ask question this time because I'm going to switch gear now into complexity theory. I wanted to do another example, binary search. Probably we'll do it another time. But I think with these examples, you kind of see how to set things up for recursion and how to approach it. And we're going to practice that in today's lab as well. Okay. So let me stop.